introduce Fabian Walter as a speaker of today's colloquium at IAP. Of course, I would have preferred that he would be physically here, but at least he will speak through Zoom. So Fabian is since, I think, 2004, a staff scientist and a group leader at the Max-Planck-Institut for Astronomy in Heidelberg, and he's also an associate astronomer at NRO and an international associate at the Cosmic Downs Center. He defended his thesis in, I think, at the end of the 90s in Bonn on the topic of the violent interstellar medium in nearby dwarf galaxies. And since then, he has developed a successful career working on galaxies nearby and very far away, with postdoctoral positions to start with at Caltech and then followed with the Jansky Fellow at NRO. So Fabian has a principal author and co-author about 600 or 630 refereed papers or so. And I had the pleasure to be part of about 90 of them. I think what is the most remarkable in what Fabian has done in his career is that he has been leading, or he has been a co-PI of a series of very important large programs and projects using various facilities, including, for instance, a search for high-Z quasars using the Pan-STARRS telescope. The project THINGS, that was a large program with NRO to perform 21 centimeter H1 observations of very large sample of nearby galaxies. And more recently, he was leading a series of co-PIs, ASPECS, which is the ALMA spectroscopic survey, and the Hubble ultra deep field, which is a 3D survey of gas and dust in distant galaxies. And this was one of the first two large programs that were accepted and scheduled with ALMA, and fulfilling hence one of the original scientific goals that was foreseen when ALMA was discussed and decided in the late 90s. There are about, including with the pilot program that led to this large program, something like 25 papers that have been published since then, based on these observations. And today, Fabian will provide an overview of the salient results and outcome of this very successful project. So in normal times, I would say, Fabian, I'll give you the floor, but today I'm forced to tell you that I'd rather say, Fabian, the screens are all yours. And so we are now looking forward to your presentation.
All right, let me start sharing my screen here. Does this work?
Yes, just a second. I'll mute everybody except for. Yes, Fabian, please unmute yourself.
All right. Okay, good. All right. Well, thanks very much, Pierre, for the very kind introduction, and thanks everybody for joining. And of course, it would be much nicer if I could be there with you today, but this is the times we live in. So I'm very excited to tell you today about ASPECS, which is the ALMA spectroscopic survey of the Hubble ultra deep field, as Pierre already mentioned, one of the first ALMA large programs. And it really had a long history, right, coming to this point where we are today. And it actually started here, I do remember, we started discussing this kind of project already 15 years ago. And then at the time, we thought that, with Plateau de Bure, it needs larger bandwidth to do this. And then we actually, once the bandwidth was there with Plateau de Bure, we actually did the first pilot programs for this project about 10 years ago. And then with ALMA, we had another pilot program to demonstrate the feasibility of this kind of research. And then it ultimately led to the large program. So I'm very excited to tell you what we learned from this survey. And before I start, I just want to highlight that we have a webpage here, www.aspecs.info. So you can just go there, look at the papers. We have lots of visuals there and movies and interactive stuff that I hope some of you may find interesting. So let me start by, of course, acknowledging the team that is behind this. It has really been an outstanding team, really covering a broad range of expertise, from the X-rays to the radio in multi-wavelength coverage, but then also having a lot of theoreticians on board who could then actually help us put things into context and to bridge from the observations to the theory. And Pierre is of course one of the core people here. This is the first extragalactic ALMA large program that was accepted. We targeted the Hubble ultra deep field for reasons I will explain in a second. This has been a 200-hour effort executed over the years 2017 to 2019. And it really, as I mentioned before, builds up on extensive Plateau de Bure and NOEMA and ALMA pilot programs. So let me try to motivate this work and give you some theoretical framework here. I mean, you have all seen these kind of cartoons as shown to the left, where galaxies start through merging systems, accretion, and then they build up the universe that we see today. And of course, we want to understand how exactly this process happened. And what has happened over the last 20 years is that there's really incredible progress in the simulations of structure formation in the universe. I'm just showing you here 8 movies from the illustrious TNG group, but all the other movies, all the other simulations to first order, to the outsider like myself, look very much the same, and that is that galaxies, they grow through gas accretion, and I would argue that the accretion gas flows are largely unconstrained observationally, and this indeed was one of the core goals of our program, to really shed more light on this by looking at the molecular gas phase that you need to form stars. To further motivate this, let me start with some plots that many of you have likely seen already. So this plot here, what's shown here is the cosmic star formation rate density as a function of lookback time. So on the y-axis, we have star formation rate density in solar masses per year per cubic megaparsec, that's co-moving. And then on the right axis, on the x-axis, we have redshift or cosmic age on the top. And as many of you know, right, there's this increase of the star formation rate density to up to a redshift, let's say 1.5 or so. And then there's this factor of 10 decrease since that. If you were talking physical megaparsecs, the decrease is of order a factor of 300. Right, and this number makes sense, right? You have one solar mass star formation rate in our galaxy, maybe another solar mass in the Andromeda galaxy, but there's like maybe 100 megaparsec volume when you look at the entire local group. So this is why you end up with this star formation rate of about 0.01 in the local universe. All right, so when you integrate this curve here, that's the star formation rate density, you get the stellar mass density, and this is shown here. If you just integrate this yellow curve here, you get the dashed yellow curve to the right. The actual observed stellar mass density is a little below that by a factor 30% or so. And the reasons for that is that not all the stars that are being formed, they stay in, they keep their stellar mass. I mean, there's of course strong stellar winds, supernova explosions. So this is this return factor that leads to the fact that the stellar mass that survives is a little below that, right? And I should really stress here, this plot to the left has been, the culmination of decades of work from red frame UV measurements all the way to the radio. And likewise here, this is also the accumulation of many decades of work getting stellar masses most reliably, of course, through rest frame K-band imaging. And there's a beautiful review written on this by Madal and Dickinson. Now, this is the stars that are being formed. So how about the gas that you ultimately need to form stars? Also for a decade now or so, or even longer, it is known that when you look at the H1 density, that's the atomic hydrogen, the neutral gas, this curve is rather flat. This curve is very hard to measure because in the local universe, you can measure H1 in absorption, in emission, right, through the 21 centimeter line of neutral hydrogen. And at high redshift, you can only measure it through absorption measurements against background quasars. But nevertheless, there is strong consensus that the curve looks sort of like this, maybe a factor 2 decrease over the history of the universe. And then, the missing component, of course, is the molecular gas density. And this is exactly what we wanted to measure with ALMA. And this is already what we sort of measured with Plateau de Bure in our pilot programs. We had this kind of region that we could constrain with the available data at the time. But of course, arguably the error bars were pretty significant, and we really wanted to improve upon this using ALMA. Now, how do we do this? We want to measure molecular gas. How do we actually do this? And let me just show you an example spectral energy distribution of a galaxy here, M82. And as you know, there is the far infrared emission, and then the mid-infrared, and then the optical and UV. If we just look at the total emission that comes out of this galaxy, now shown here in gray, it's in the far infrared where we can actually measure the molecular gas. Okay, and we do this through both molecular line emission, but also through the dust continuum. And there's, for example, the CO line that we use, but there's other lines, C1, C2. And this is the regime that we are looking at when we want to observe molecular gas at high redshift. And of course, this is exactly what we did with ALMA. Now, why could we do this measurement only now and not, let's say, 10 years ago? And there's really two enabling elements for this. And one is the existence of the Hubble Ultra Deep Field, okay? So this is the field that has the deepest multi-wavelength data with, literally thousands, almost 10,000 of well-characterized galaxies at essentially all redshifts. And, any telescope that you can think of spend hundreds of hours on this field, right? So if you want to do multi-wavelength composite of galaxies, this is the field that you want to study. And it's, of course, unfortunately in the south, unfortunately for the northern facilities. And it also has, incredible MUSE coverage. This is the VLT integral field unit, and lots of HST, Grism long spectroscopy. I just want to show here, this is a typical SED of a galaxy in this field. It's really beautifully sampled SED, so we can derive galaxy properties immediately. Now, the other enabling element is, of course, ALMA, because you do need the sensitivity of ALMA in the continuum for sure, but also in the CO to trace the dust and the molecular gas in the Hubble Ultra Deep Field, which is very well visible from ALMA, right? That's another reason why ALMA is the instrument to do this measurement. So this is what we did. We looked at the UDF and we observed two frequency bands here, the band 3, which is the 3 millimeter band, and the band 6, which is the 1 millimeter band. This is shown here in this graph here, ALMA band 3, 3 millimeter band, ALMA band 6, the 1 millimeter band, and we observed the entire bands, which meant we needed a couple of tunings for each of these bands to cover the entire frequency range. Now, when you do this, right, what you see immediately here is we plot here the observed frequencies of various CO lines, which is one of the main tracers that we use to measure the molecular gas. This is the redshifted behavior of the CO 2 to 1 line, 3 to 2 line, 4 to 3 line, and so on. And you can see when you cover these two bands here, ALMA band 3 and ALMA band 6, you essentially cover CO emission at all redshifts, all the way to very high redshift. And so this, I really feel like this is fantastic and sometimes not really appreciated because, yes, interpreting the results will depend on the excitation of the CO and the temperature of the gas. But still, we have one single molecule that we can use to make this measurement, modulo some things that we need to understand about this molecule. But this is, of course, much better than in many other fields where we have different traces at different redshifts. So then we looked at the deepest part of the UDF, which is called the XDF, which is this with our band 6 and band 3. And sometimes when you talk to optical folks, right, they refer to single HST pointings as, pencil beam surveys. If that's true, right, then what we are doing are very sharp pencil beam surveys, because the ALMA primary beam is much smaller than the ACS or C3 coverage of Hubble. In fact, we needed 17 and 85 pointings to cover the XDF, right? So now I want to show you the actual data. So what you will see now is our actual data overlaid on the Hubble Ultra Deep Field. What I'm doing is zooming into the Hubble Ultra Deep Field, overlaying now the entire 3 millimeter data cube. And now what we will do is we will rotate this data cube along the z-axis, and the z-axis is frequency. Okay, and I hope you can see it over Zoom that there's these islands of emission here, and these are line emitters, right? These are line emitters in our field, and in most cases, these lines are the CO lines. And of course, there's lots of faint emission in the noise that we also dig out through various techniques. But this is the data, and then we can overlay it again over the HST image And this is what we deal with. So this is actually a lot of data, 2 big data cubes. We have lots of terabytes on our disk. In addition to this, a beautiful ALMA data cube, and actually we have 2, one for band 6 and one for band 3. We also have a MUSE data cube. And again, MUSE is now the optical integral field unit from the VLT that covered the same region on the sky in more than 100 hours of integration time. And this has been instrumental for us doing the cross correlations between the ALMA data cube and the MUSE data cube to get good identifications for our sources. Because remember, right, if you only see one island in the sky before, right, I mean, we saw the CO lines, we don't know a priori what CO line that is. That could be any J transition, any rotational line. And just to summarize again what I just shown you, I have shown you this band 3 data cube from ALMA. We also have the band 6 data cube. And you can already see in the band 6, we see these linear features here. And these are just strong continuum emitters, right? If you have a strong continuum source, you will see it over all the frequencies. This is, of course, something we need to take into account. Now we can ask which of these islands here, which of these blobs belong to which CO transition. And this is just a histogram shown here to the right. And not unexpectedly, when you are in the 3 mm band, you mostly see the low J lines of CO. And then when you go to the 1 mm band, you see mostly the high J lines, right? So this is just a distribution of the line fluxes. Now, these are the lines, but of course, we can get a very deep continuum map if we just collapse all the cube along the C axis, the frequency axis. Of course, before we do so, we want to remove all the bright things so that we get a pure continuum image. And this is shown here, which is now our final continuum map of the Hubble ultra deep field at 1 mm frequencies. And the RMS is a little better than 10 microjensky. So this is the most sensitive dust emission map of the universe over this significant area on the sky. And when you go to our webpage, we have some nice visuals here that we use for public talks, but maybe some of you will also find this interesting. So this is what ALMA gives you when they look at the same area on the sky as the UDF with Hubble. Okay, so the question is, of course, which of these galaxies that Hubble sees are actually the ones that ALMA detects? And these are highlighted here with different colors, depending on whether we detect them in the dust continuum or in the CO line. And I will talk about these in more detail in a minute. But before I do so, I want to remind you that these sort of blind deep surveys of the sky is not the first time people have this idea, right? So any bolometer map, for example, starting in the mid-90s or late 90s with SCUBA, and then later on with MAMBO and SCUBA 2 and La Boca on APEX later on, do the same thing, right? You just cover some area on the sky and you look at the source that you detect. Of course, with a bolometer, you have no redshift information. You only have one continuum map. And this is one example here. This was at the time the deepest map in existence of the extended 100 deep field south. And what you do is when you get these kind of maps, you ask, okay, how many galaxies do I see above a certain flux level? And these are the number counts that people have looked at for decades, really. And the point I want to make here is that when you now compare this to the ALMA measurements, right, is what I'm trying to attempt here, we observe really very different beasts now than before, okay? So these were here in this regime, the plot I just showed you, the classic SMGs, sub-millimeter galaxies, with fluxes of many milligenskys in the sub-millimeter, and this corresponds to 1,000 solar masses per year star formation rates or more. This plot now that I will show you is from a very nice review by Jackie Hodge and Elisabetta Cunha, just published last year, that already include our ASPECS data, right, our large program data, which is shown here. So the black data points here is now the ASPECS data points from our survey. And there are two things I would like to highlight here, right? First, with ALMA, we really go 2 orders of magnitude deeper than any previous study, okay, with the bolometers. So these, what we are looking at here, are not sub-millimeter galaxies, or at least not your traditional sub-millimeter galaxies. We go to star formation rates that are vastly below what was previously accessible. And the other thing I want to just highlight here is that when you look at the previous studies and compare them with our studies, right, that the number counts went down a little, or actually by a lot. And it's also fair to say that we expected to detect more galaxies with ALMA than we actually did, and we were not alone, right? Other folks, other groups have done simulations extrapolating how many galaxies ALMA would detect, and they all came up with larger numbers because, you know, the faint end slope was not very well determined. So this, you know, this also implies that if we added a lot more observing time here, we only would recover very few additional sources, which is kind of frustrating. I will get back to that at the very end. But this gave us, you know, some pause and you know, time for reflection, and we really try to very deeply understand our maps and ask, you know, is there maybe any emission lurking behind our sensitivity threshold, or is this shallow slope that we see indeed the final word? And the answer is yes. In order to do that, you know, you need to have a very good understanding of the noise properties in your map. And, you know, the volumeter folks have done this for decades, you know, when they jackknife the data. So every second scan, the amplitude will just be multiplied by -1. So the noise properties remain and just the signal goes away. We've done the same thing here with the ALMA data, I believe for the first time, where we switched every second amplitude of the visibilities by 180 degrees. The phase by 180 degrees. And thereby, all the signal is canceled out. You can do the same thing by randomizing the UV phases. And when you do that, and you look at the resulting noise properties in your map, and we did, of course, many realizations of these, it's a perfect Gaussian. It's just beautiful. And then you can inject sources to this Gaussian or to this noise field, and thereby also, you know, constrain the flattening of this curve. And it turns out that what we find here is exactly compatible with what we derived through the number counts. So this is a technical slide, but I hope that, you know, people will pick up this technique to, you know, characterize the noise in interferometric data by the jackknifing of the UV data. The second thing is, you know, are there galaxies just lurking below our sensitivity limit? So in order to assess this, we did numerous tests that are also published in various papers. One is, you know, we did stack the dust continuum sources. We have thousands of galaxies in the UDF, so we can just bin them up in redshift bins or stellar mass bins and just ask, is there any additional signal in the galaxies that we do not individually detect? And the answer is not really. You know, below a stellar mass of 10 to 9.5, we hardly detect any signal. There's little additional emission recovered through the stacking. We also did CO stacking. That's a little bit more complicated because in addition to the location on the sky, you also need a redshift of the source, which we get from the MUSE data. And by stacking those data again, you know, stellar mass, and here now plotting as a function of main sequence location. The bottom line is we see the same thing. We do not recover any additional CO flux below a stellar mass of 10 to the 10. And then we also did cross correlations between the ASPECS and MUSE cubes. Another paper that we published last year. And, you know, you can do this cross correlation between the color logs including all the ALMA detections, and then you get the signal that you see here in black. And then when you remove all the detections in ALMA, you hardly end up with any signal, which really means there's little power after removing individual detections. And then to go back to our questions, to our question up here, are there other galaxies just lurking below our sensitivity limit? The answer is no. Okay, now let's move on to asking what kind of galaxies do we actually see. First, I want to show you the CO spectra of our galaxies, and just to, you know, impress you how beautifully detected these galaxies are. So ALMA really has the sensitivity to provide us with these remarkable spectra, and then I'm showing some overlays on the HST images here. So what I would like you to take away from this is the galaxies that we detect really cover a range of properties in the HST morphologies. Some are very red, and some are like spiralish. Many of them are in crowded regions. And, you know, this is entirely a molecular gas selected sample, right? We didn't know which of these galaxies would show up in CO. So these are the ones that do show up. And all of the galaxies that we see have near infrared counterparts. You know, we don't see any HST dark galaxies, okay? And I believe the only reason why that is because we're looking at the UDF, right? So these are the galaxies for which by far the deepest photometry exists. for any of the objects. Okay, so now the question is, this is CO, but we would like to have molecular gas. And there's, of course, this old debate on how to best do this. And I try to summarize this in just one slide. I should mention that we also derive the molecular gas masses through the dust emissivity, but I will not have really time to talk about this today. The upshot is that the results are very much comparable between the CO and the dust emission. Right, so you have a CO line, you want to get a H2 mass out of it. And for that, you need two assumptions. You need an assumption about the metallicity of your gas, and then you need an assumption of the excitation correction, because the CO to H2 conversion only really works for the CO ground transition, the CO 1 to 0 transition. Let's first talk about the metallicities. Now we are in this extremely luxurious situation that we actually have metallicity measurements for many of the objects in our sample. And this is from the MUSE data. And it turns out that to first order, the objects for which we could determine metallicity, they do have solar metallicities or around solar metallicities, which then prompted us to use the galactic conversion factor, which is the one that you should use for galactic, for solar metallicities. So this is one thing we did. And the other thing is the excitation correction. And again, we are extremely lucky here in the regard because we can actually measure the excitation in many of our targets. Because through our scan, we have multiple CO lines in our scans in many regions. It's just one example. And then we also did VLA follow-up observations. And in many cases, we also have a CO 1 to 0 detection. So we can put this all together and construct, spectral line energy distributions for all the galaxies in our map. And this is sort of what we get. These are average excitations for the redshift 1.2 and 2.5 bin. So we have a pretty good handle on these excitations. This is all I would like you to take away from this. So with this, we can actually estimate the ground state CO flux, the CO 1 to 0 flux, and then with our metallicity estimates, we get an actual H2 mass out of this. Now, I want to put the galaxies that we detect in the UDF in context with other galaxies that have been observed through many other surveys. For example, let's concentrate here on the redshift distribution. Right, what's shown here in black is our ASPECS sources. And then you can compare this, for example, with the SMGs, the submillimeter galaxies. They peak at much higher redshift. Okay, they peak at redshift 3 or so, whereas ASPECS peaks at around redshift 1.7. Now we can ask the galaxies that we observe with ALMA, where do they lie with respect to the so-called galaxy main sequence, right? So galaxy main sequence means if you plot the star formation rate on one axis and the stellar mass on the other axis, then to first order, this is coded by redshift, there is a main sequence of galaxies indicated here by different colors for the different redshifts on which these galaxies, the main sequence galaxies, reside. Galaxies above this are starburst galaxies. Galaxies below this are the more quiescent galaxies. And what you see immediately here is that we find galaxies above, below, and on the main sequence, which is, of course, a direct consequence of how we selected the galaxies, right? We did not select them using any of these parameters, not the stellar mass, nor the star formation rate, because we're just doing a blind scan of the entire UDF. So, I mean, there's lots of studies of individual galaxies, and most notably, of course, the really fantastic efforts using Claudio de Buhr and now Noema for the FIPS 1 and 2 teams, work led by Linda Tacconi in particular. So we can, this is now the blue contours indicating where the FIPS galaxies lie in this diagram, where we plot the star formation rate on one axis and the molecular gas on the other axis, and then overplotted to this is our galaxies. And you see that there's, actually very good agreement. And the depletion times are of order 1 giga-year in both cases. So then we can move on and ask, the gas mass fraction. This is just dividing the gas mass by the stellar mass. This number is about 10% in the local universe, but then it increases to about unity at redshift greater than 2. And what we find is, again, very much comparable to what previous studies have shown. Now, let me move on now to actually constraining the CO luminosity H2 mass functions, because the ultimate goal that we have in mind is, of course, we want to get the molecular gas density This is the entire reason why we're doing these scans of the Hubble ultra-deep field. So just as a reminder, right, I've shown you this graph before. Let's say if you look at the CO2 to 1 line, this is the redshift range that we cover in this line, okay? And then we can just ask, we can measure how much luminosity in CO do we see, and this is indicated here in red. This is our ASPECS measurement, and the other curves, the other bars here indicate previous measurements also obtained with plateau de Bure. Right. So for CO2 to 1, this gives us 1 redshift bin. So we just measure all the flux that there is in this redshift bin, and this we can translate to an H2 mass, as I have discussed before. Okay, now we have, of course, also other redshift bins, right? We see the CO1 to 0 line here. This is CO3 to 2 line, 4 to 3, and so on. And then we can just build up these luminosity functions in these 4 different redshift bins: 0.3, 1.4, 2.6, and 3.8. So again, the red curves here, or the red area, indicates our ASPECS measurement. And just as an aside, there has been another survey done with the VLA, so lower J transitions, completely different field. Actually, there was most done in the Cosmos field, and there's actually satisfactory agreement between these 2 surveys. But I would really like to stress, we cannot constrain the faint end of our luminosity function with the available data, right? But we know that the faint end slope cannot be steep, because otherwise we would have recovered this through the stacking that we have done earlier. Okay, so the next step is then to just integrate, sum everything up that we see here, right? So we can just integrate all these masses in these different redshift bins, and that gives us, because the volume is well defined, right? We know what the volume is for this particular CO transition, or this particular CO transition. So we just sum everything up, and this gives us this final plot. This is the evolution of the molecular gas density. And again, what I'm showing here in red is our ASPECS measurements. And what I should really show here, which I actually should add to any future presentation, is our proposal that we wrote at the time. And it turns out that our error bars are very similar to what is shown here, because we really wanted to constrain the peak of the density here, and also the increase and decrease with time. So this is very good. And if you compare this to other endeavors, there's, I would say, to first order satisfactory agreement. And there are details why these curves don't always look exactly the same. However, when we compare this to our ASPECS analysis using the dust continuum, a paper led by Benjamin Magnelli, we get very consistent results. Okay, so now, one way we demonstrate in public talks how we do this is through this movie. So please forgive me if this is maybe too basic, but it sort of nicely summarizes how we are actually making this measurement, right? We start again with the Hubble ultra-deep field. Now we actually rotate the field, but we order by redshift, not by frequency. So these are the actual redshift distributions. We now indicate by color which of the galaxies are detected by ALMA. Okay, and these are now the brighter and the not so bright orange colors. And then we basically zoom out, and then we just basically collect all these fluxes, right, in various redshift bins. And this is how we build up the final curve. And of course, the devil here is in the detail, and we do lots of statistical analysis to deal with sources that are very close to the noise, etc. But this just gives you an idea of how this measurement was done. Now, let's talk about cosmic variance, right? Because this always comes up when people study the UDF. The UDF is very small on the sky, right? It's about 2 by 2 arc-minute square. And that is, at redshift 2, this only corresponds to 3 by 3 co-moving megaparsecs. And we know, of course, if you look at the illustrious redshift 2 simulation, that cosmic structures varies on such scales, right? There's no question about it. But the key is really that we cover a very significant volume here through this scan, okay? We cover 40,000 cubic megaparsecs. And this we have discussed and motivated in many papers, and also in the proposal, of course. But this is something we knew for a long time, that the area projected is small, but of course the volume that we cover is huge. And it turns out that the measurements that we do are entirely limited at this point by Poisson errors, because we don't detect thousands of galaxies, but maybe a few dozens, okay? Now, this is one thing you can look at these numbers and say, yeah, okay, that makes sense. But what gives me peace of mind is the following, right? Imagine the UDF was the only region on the sky that you observed, for which you know the galaxy properties. Forget about the cosmos and big candles and all these big wide area surveys. You only have the UDF. You can ask, what is the star formation rate density that I derive from just looking at the UDF galaxies? And this is what you get. These are the blue points here, and that the full red points here, and you can then immediately compare them to the cosmic average. So these are the numbers that come from very wide field surveys, right? And so I would say the UDF only star formation rates are indeed in good agreement with the cosmic average, and then we can just proceed to the next step and put our measurements in context with the previous measurements. And this plot I've already shown you earlier. This is the measurement we wanted to do, and I've just shown you. This is exactly what we derived. This is now a fit to ASPECS on all the other available data. But if you only fit to the ASPECS points, we get essentially the same result. So this is now the molecular gas density that we now have here for the first time. Okay, so now we can put this all together and plot everything on the same plot. The cosmic mass density here on the y-axis, on the x-axis is the redshift. And just for convenience, we also plot the cosmic age here on the top x-axis. And what you see is this is our H2 measurement from ASPECS. This again is the stellar mass buildup through cosmic time. And then as a reminder, the H1 was relatively flat. And then when we add all these baryons together, we get this black curve. Okay, this is the growth of baryons within galaxies. So at about a redshift 1.5, the stellar density took over in galaxies, right? At redshifts lower than this. Okay, now let's look at this in a little bit more detail. We can start at redshift 1.5, which is the peak of the star formation rate density, and we can ask how much stars are being formed from that period on, like 4 gigayears after the Big Bang to today. This is this shaded area here. And we can compare this to the H2 loss, the molecular gas loss. Now, this is a log plot, so it's kind of confusing, but it turns out when you plot this in a linear space, I should really reverse the order here, but now this is redshift 1.5 here, and we move forward to redshift 0 here. This is the mass in stars that is being formed, right? And then the molecular gas that is being lost is only the blue curve here, right? So in other words, with the molecular gas that is available at this time in the cosmos, there's no way you can form all the stars that you see today. And of course, this argument has been made in different ways many times before. This just means you need accretion to the galaxies. Otherwise, you just cannot build the galaxies that we see today. Now, we came up with a very simple model here, basically using observational data that we compiled through earlier surveys. Pierre already mentioned the THINK survey. We also did the Heritage survey, the ERAM 30-meter follow-up survey, the atomic gas, molecular gas, and the star formation rate of many, many galaxies. And what you always see is that the molecular gas is associated with the star formation rate to first order, and then the atomic gas is more extended around them. And this is also seen in high redshift simulations and observations. So we came up with this very simple cartoon, which again is on our webpage if you're interested in this. It's just showing the same thing, right? We have the stars and the star formation in the center with the molecular gas. This is surrounded by atomic gas. And then around this, of course, we have the CGM and the IGM, where a lot of gas is in the ionized phase. And now with this in mind, we need a net accretion process through these phases to the center. And yes, there are also outflows. That's why I call them net accretion, right? Because the accretion needs to dominate. Otherwise, you wouldn't be able to grow the galaxy that we see today. And you can come up with a very simple set of equations here to actually describe this process. Keeping in mind that the universe is actually a closed box, right? The mass in baryons is approximately constant if you just ignore, some tiny fraction of the mass is lost due to the fusion process. But you could now, in a very simple universe, think, okay, we have stars, right? We don't know where they are. They're just stars. There's molecular gas. and there's ionized gas, and then there's atomic gas. And in principle, right, there could be flows between all these different phases. And these are just written down here. So a very simple set of equations. Now you can simplify this set of equations by, having some having some assumptions here. For example, let's assume that ionized gas cannot form stars immediately. Okay, and then we have described this in this paper shown down here. You can really simplify this set of equations to a more manageable set, and then of course also just having net flows and not accounting for the extra complication of outflows. Now, when you do this, you can actually really calculate the flow rates from the ionized phase that you need to go to the H1, which is the more extended phase in the galaxies, and then from the H1 to the H2, which is in the more central parts of the galaxies, right? This immediately comes out of this equation, and it's a function of these observables, because we measure rho H2, and then we can, of course, measure the first derivative of this. We have measured rho H1, and the first derivative, and the star formation rate density has also been measured by many folks. So this is shown here, where these are just our measurements from ASPECS and the previous H1 measurements shown in blue and in red. And then these two net inflow rates are shown here in different colors, okay? And this is great, because now we actually have some first constraints on what are the actual flows that need to be entering the galaxies, first from the ionized phase to the atomic phase, and then from the atomic to the molecular phase. And of course, we do this because we want to put this, coming back to the first slide of my introduction, we really want to compare this to simulations so that we can learn from the simulations, and likewise, we can hopefully inform the simulations. So we can ask, are the numbers that we calculate, that we derived from our very simple approach, do they make sense? Are they reasonable? Well, that's the question, right? Are the H2 accretion rates from the IgM, for example, or the CGM reasonable? Here, I'm just plotting the ionized gas that we need to accrete to form H1. So what we did is, this is exactly the plot I've shown you before. Now, we compared this to simulations and that show the baryonic matter accreted on dark matter halos. Actually, the simulations give us both. They give us the total amount of matter accreted on the dark matter halos. These are the dashed lines here. And then, of course, only a fraction of this will be baryonic matter. So this is just multiplying these dashed curves by 4% or so. And then you get these numbers here, which is the baryonic matter in the simulations that are being accreted on the dark matter halos. And now from our measurement, this is how much of this ionized gas actually ends up on the H1 disk of the galaxies. Is about 10 to 30%. I wouldn't dare to say this changes as a function of redshift given our uncertainties, but this is sort of, I think we're in the right ballpark here, right? That of all the accreted material, of order 10 to 30% of the net material will then end up in the galaxies. So let me just have a few more slides and then I will wrap up. So if I go back to what I've shown you before, I've shown you these plots before, exactly these curves, but so far they were in logarithmic, sort of in redshift space, and not in linear cosmic age space. So this is now linear cosmic age, and redshift is now here on the top. We can't say much above redshift 4, but then this is how we think things evolved over time. Again, the molecular gas density is doing this. The stellar mass buildup is doing the red curve. And now, there's no underlying physical model here, but if we just simply extrapolate these curves, this is what you get in the future, right? So this immediately implies that most of the baryons, right, which we see here, they will actually stay outside the galaxies, okay? And this means, this decrease in accretion rate means that the feedback is less relevant, and it's also due to the expansion of the universe, right? It's just harder for material to enter the galaxies. This has nothing to do with an accelerated accretion of the universe. This is just your normal accretion of the universe. It makes it harder for stuff to fall onto the dark matter halo. And as a consequence, over the next Hubble time or so, the accretion will go down, the star formation rate will go down, and then this is what Chris Carilli refers to as the cosmic sunset. And this is just one slide that shows the same thing, maybe a little bit more attractive for planetarium shows, etc. We have on this webpage other things that you may be interested in looking at, how the pie charts, how the fraction of the different baryonic components change as a function of look-back time. There's also little sliders on the webpage that you can use to play around with this. So I already mentioned lots of ASPECS publications in passing. There's many more that I could not talk about today, but I just want to highlight again, when you go to our webpage, we have all the papers out here. And you can just click on these links and it brings you to the relevant papers. We also now have made all the data publicly available. This is all the calibrated UV data, all the mosaic data, the frequency stitch data, the cubes and the maps, everything, the tables from the papers is all available for download. And we really hope that people use this for further analysis. So then let me just summarize real quick. We got the deepest map of cosmic dust and gas with ALMA on the Hubble ultra-deep field. With this, we can put individual galaxies into immediate context with other galaxy populations that have been studied before. We could constrain the missing component in the baryon cycle with error bars that now really allow meaningful derivations. And that helped us to constrain the gas accretions, actually the first constraints of this kind on the gas accretion process. Now, I don't want to end with a downer, but I do want to say that obviously by doing this, right, it's the first full picture of the density evolution, but we are obviously greatly averaging over time and space, right? We're averaging over many, many cubic megaparsecs and over billions of years to get these results. And we, of course, want to do this, we want to break things up in smaller pieces and, making things as a function of stellar mass or dark matter halo. So the next major step, really needs much more than 10 times larger samples and areas than currently covered. So now when you think about this, right, this means you would need 2,000 hours or more of current ALMA time, right? This is a very, very significant request. And it's, I think, very unlikely that we can ask for so much time in the next future. I mean, there are some solutions out there, right, to actually help in this process. Remember, we do a lot of frequency stitching together, right? We observe the same field again in different frequency setups. We do lots of different pointings to cover the area that we need. Now imagine if you had receivers that had broader bandwidth, right? And I will point out that NOEMA already has twice the bandwidth of ALMA. There are attempts to double this again at NOEMA. And the ultimate dream, of course, to have focal plane arrays, just not one beam, but already 4 beams would be awesome, right? You don't need 100 beams, but that would already very significantly speed up the process and has huge applications, not only for this field, but for many other fields, many galactic studies, etc. So there's lots of preparatory work done, in particular at NOEMA, where having 4 times the ALMA bandwidth is in immediate reach. And there's, of course, the dual band capability. The correlator is already almost ready, waiting for deployment. So then you get 2 bands at the same time, which again speeds up the process by a factor of 2. And at the 30 meter, of course, there's a multi-beam technology being developed on very small aerial scales that potentially could also be deployed at some point in the future for NOEMA. And of course, then there's ALMA 2030 roadmap, and in the maybe more distant future, the next generation VLA, which will have a 3 millimeter capability and will have 10 times the collecting area of ALMA. But with this, I would like to end, and I'm very happy to take any questions you may have.
Okay, thank you very much, Fabian, for this fascinating talk. So if you have, Henry has a question.
Thank you very much for the great talk. Can we go back to the plot of the molecular gas mass density as a function of redshift? I was trying to understand, why are you so different from the Scoville et al. Result? Is it because of the way the 2 samples were selected?
Yeah, let me just find the curve. Right. So there's two things here. There are the biggest outlier that we have is indeed the Scoville points here, right? Yeah. And then there's also A3 cosmos up here. And so, there's a very simple explanation, I think, for both of these. First of all, I mean, Scoville, they only looked at, sub-millimeter galaxies, right? They did follow up the brightest galaxies in the cosmos. And therefore, they had to extrapolate to the galaxy population that we now actually observe, right? So it's different samples. And I would just argue with the knowledge that we have now, Nick would have reached other conclusions with the data. But with the data available at the time, this is indeed exactly what you would learn. And I think we are just, factor 2 or so below. For the A3 cosmos, it's a matter of how you deal with the faint end slope, right? So they also extrapolate, and they go much deeper, and they have a much deeper faint end slope than we have. And I think, we have very well constrained this through the stacking. We know that it cannot be very steep. And this gives rise to this quite dramatic, very uncomfortable discrepancy here. But we have checked this many, many times, and we feel like I should note, right, just to be very clear, in the previous slide, I've shown you the data that goes into this, right? This is what goes into it. So we are not extrapolating towards higher masses or lower masses, okay? So we are taking the emission that we have, and the reason why we don't extrapolate is for the more massive sources, right? The SMGs, they play no role in the cosmic density, right? There's very few of them. Yes, they're brighter, but they're few. So they actually don't count. And then for the faint end, I already described that, there's hardly any emission that we recover. Second.
Okay, thanks. Thank you again for a very nice talk.
Oh, thank you.
Pity we can't see you at EIP.
I will come visit as soon as I can.
Okay, thanks again.
I'll invite you, Fabian.
Christophe has a question too.
Hello, again, excellent talk. I'd like you to clarify, and I'm not sure I understood what you said about the fact that you have an excess of stars or an excess of baryons outside of galaxy. Which was it?
Sorry, maybe I misspoke, but you're referring to this plot, I think.
Yes.
What I wanted to say is that when the universe was young, right, the gas was dominating the dominating part in the universe, and then only as time moved on, the stellar mass increased and increased. It's just adding more and more mass, and at this redshift 1.5, the mass in the stars in the galaxies then dominate the baryon budget within the galaxies. All that we are looking at here is all within the galaxies, all the baryons in the galaxies. Does that make sense? And then, of course, you keep growing the stellar mass, and that's why in the local universe, right, the stellar mass always dominates the baryonic mass in galaxies.
Okay, but did you say or did you not say that there were lots of stars outside galaxies?
Well, if I said this, I certainly didn't mean it. I mean, the stars, the assumption is that the stars are all within the galaxies. And this is also, what the HST images show us, right? There's no evidence for a large fraction of diffuse stellar light around these galaxies. So yeah, maybe I misspoke, but the stars, so the stars
I'm not saying that. You're also saying effectively that there's a large amount of baryons outside of galaxies. The difference between your dotted line and your black line, I guess.
Exactly. That's right. Exactly. That's one of the. This has been pointed out before, obviously, but now that we have this good constraint on the molecular gas, we can make this a rock solid result. And the final slide that I showed, right? Again, right, I need to stress that this is not a physical model when we extrapolate these things, but it's just guiding your eyes. It means there's no way, that there's a lot more stars being added to the current universe, and which means that most of the baryons will indeed stay outside the galaxies.
Okay, thank you very much. Thanks again for an excellent talk.
Thank you.
Okay, now Marta has a question.
Yes, it's mostly on the first part of your talk when you showed the log n log s, and you said that you know, it was flattening, so you didn't expect much more going deeper. Yeah. So can you, I think that, you know, by the end of your talk, you put this together, but can you, in any case, give us a feeling of how it is in, sorry, at other wavelengths? So do you see the same type of flattening if you go to other wavelengths? And,
so, I mean,
yeah, is the flattening as strong as this, or?
Well, thanks very much for asking. And this is one of the papers that I did not have time to actually talk about. Is a theoretical work by Gergo Popping. So what you could say, you know, we have a very good understanding of, you know, stellar masses and star formation rates of galaxies. There's lots of studies and catalogs of this. And if we just had taken these, for example, the Baruzzi catalogs, right? The what is it called? The universe. The name escapes me.
Universe machine.
The universe machine, exactly, right? So what Gergo Popping did, he took that data from the universe machine, and then he just plugged in the you know, typical scaling laws for gas and dust, and he came up with exactly this behavior of the flattening. And what we see here is the flattening of the stellar mass function at redshift 1 or 2, because all our black data points here are actually galaxies between redshift 1 and 2 to first order, right? There's some outliers, but that's where the bulk comes from. And this is exactly the flattening. What the flattening you see here is exactly the stellar mass flattening that you see in the mass function as well. So in retrospect, you know, we should have done this earlier, and then we would have gotten the right answer before. But this was one of the cases where you do the work later and you're like, okay, now it all makes sense. And he did not, I mean, when you read his paper, he really did not tweak any of the parameters here, right? He just got this straight out of the simulations.
Thank you.
Okay, other questions?
Yeah, can I ask a question?
Yeah, go ahead.
So thanks, Fabian, for your excellent talk. And I'm impressed that you summarize everything, like 15 years of work in 40 minutes. It's impressive. I want to make, I had a question about the future. I mean, you clearly delineated, you know, the difficulty to go further and the need to have a lot of hours or new equipment and facilities. I was wondering if there's also, you know, future paths in exploring in more detail the sources that you detected in the Hubble Deep Field, and what are the plans to do that and to understand better their physics, et cetera, et cetera.
Right. No, you're absolutely right. I mean, I should have mentioned earlier, you know, when you look at our maps of the UDF, let me just bring it up again. All these galaxies that we see here are spatially unresolved, or almost all, okay? So this is because we used ALMA in a configuration that was very compact. We didn't want to resolve the emission because we knew galaxies will be faint, and by resolving galaxies, you know, at the sensitivity limit, you may lose detecting them. So by definition, we have a 2-arc-second beam, and we don't resolve these galaxies. Okay, and now you're absolutely right. What the next step is to actually spatially resolve these objects with ALMA. Right, we don't need 180 pointings for this because we know where to point now, right? We would go to these sources, and we could get higher resolution imaging in both the dust continuum and in the CO line. And indeed, you know, if you look at the ALMA requirements as of like 15 years ago, right, it was like the imaging of a Milky Way-like galaxy at redshift 1 was one of the big drivers. And I think it's unfortunate that to this very date, as far as I know of, right, there is no main sequence galaxy at redshift 1 or 2 for which a very nicely, you know, spatially resolved map exists from ALMA. And the reason for that is that it's very expensive, and you need, you know, many tens of hours in the continuum to resolve the galaxies, and you actually need, you know, approaching 100 or more hours to do the same job for a typical main sequence galaxy in CO. So this is, you know, I think lots of groups are waiting for the day where, you know, ALMA is willing to give up, you know, more than, you know, the large program category would be moved from 50 hours to maybe something bigger, so that then if you ask for a few hundred hours, or even 500 hours, right, for imaging, maybe beautiful imaging of some high-redshift galaxies would not be completely ridiculous. But I think we're not there yet. It's a matter of observing time. ALMA can do it. I mean, there's no question ALMA could provide this information.
Yeah, thank you. A great talk.
I assume Christoph already asked his question. So Norma.
Thank you very much for this excellent talk. I would like to come back to one of the previous points. I mean, the unexpected flattening. In your slide, you showed, you answered that connecting it also the same effect appears for stars and the stellar, and I understand that, of course. I would like to ask you which is your understanding on this, the physical effect for this flattening you have with all this, which I think is a very interesting effect. In fact, I used the Hubble IST, you mentioned before, and the frontier fields, to use the number counts of the galaxies at high redshift to constrain dark matter, not the baryons as you did. So to show the powerful of all this, I'm very happy with your presentation. So please. And the other point, I would like to ask is also the other, you emphasized it very clear, the cosmic baryons outside the galaxies. So the trivial explanation would be because of the expansion of the universe, the trivial set of some we could see the expansion and so on. But on the other hand, we know that, all these simulations in galaxy evolution and formation and so that, to try to fit observations need to introduce a big feedback from baryons. And so perhaps you have, some things to say about. Thank you.
Well, thank you very much. To answer your first question, right, regarding the flattening, this has been long known in the stellar mass function, right? That you have this break, and this is also reproduced by simulations, etc. This is, my understanding, this is also a consequence of what you just mentioned in the latter part of your question of the feedback, right?
Yes.
That you have, just at the lower masses in galaxies, you have stellar feedback. And then at the very high mass end, you have AGN feedback, and that then gives rise to the stellar mass function that we observe. So I think in that sense, there's nothing new we can learn here. It's just that this is just, another manifestation of exactly that stellar mass function. So the other question, I'm not sure I completely understood, because yes, there is absolutely, feedback is completely essential in driving then the internal properties. And this is also what I stressed at the very end of my talk, right? That we are here really averaging over dramatic scales and galaxy properties, right? So this is a first attempt to put these things in context.
Yeah.
And by having more observational constraints, we could, the set of equations that I showed you, where basically, since we know that there must be inflow, we just talk about net inflows and just ignore the outflow. Of course, this can be elaborated much more if we had additional information on these outflow processes.
Thank you.
Okay, are there other questions? So let me stop the recording.